What I'm going to talk about is just a basic overview of representation theory of finite groups. So before starting with that, let us understand what is the subject is all about. So group theory as a whole is an abstract kind of a object. We just have 4 axioms and nothing else. On the other hand, linear algebra has lots of structures. So the point of representation theory is that we will take each group element and associate it with some linear transformation, and then try to find the properties of the group from the linear transformation. Precisely, definition of representation is the following. So, by the way, whenever I am writing G, it is a finite group, K is a field, and V is a finite dimensional vector space over a field, over K. Okay, so a representation of G is a tuple V rho, where V is a vector space and rho is a mapped group homomorphism from G to K automorphisms of V. So for example, number 1. So if I take V to be any vector space and take this map as sending everything to identity, then it is called the trivial representation. By the way, is my handwriting visible? Number 2, suppose G is acting on a set X and take V to be a vector space which is made of the elements of X as a basis, and then set rho G to be multiplication by G, that is rho G takes X to G dot X, where this dot denotes the action. Then the corresponding representation is called the permutation representation. And in the special case, when G acts on G by left multiplication, it is called the regular representation. And the symbol for this, that is in this case, will be denoted by this symbol kg. We will focus more on this kg because of the following reason. First, we have an augmented K algebra structure on this kg. That is given by this multiplication. And the augmentation map is given by sending every lambda g to summation lambda g. This is a map from kg to k and will be denoted by epsilon. Okay. So with respect to this multiplication structure, which is giving a K algebra structure, and this augmentation map, we will call it the group algebra. This term was coined by Frobenius in 1897. And why is that important? That is because of the following. So we will first try to make some connections between representations and KG modules. So consider a representation V rho. Then note that for each G in G, you can have a map from KG to, so you had a map from G to odd KV. And G are the basis elements of KG. Therefore, it extends to a map from KG to NKV. NKV means the endomorphisms of V as a K vector. And then NKV acts on V. Therefore, V becomes a KG module via this map. On the other hand, suppose we are starting with a KG module. Then M is naturally a K vector space, and we have a left multiplication which is inducing a map from KG to NKM. This is given by left multiplication. And then restrict it to G, since elements of G inside KG are invertible, therefore it will end up inside automorphism, and thus giving us a representation. Moreover, suppose we are given two representations V rho and V prime rho prime. linear map T from V to V prime is called an intertwining map if for each G inside the group, this diagram commutes. Observe that if V is a K vector space, V is a KG module, let's say, then any linear map T from V to V is KG linear if and only if it is intertwining. That is just the definition. Okay. So with respect to these 2 points of view, where I have taken a representation and compared it to a KG module, and intertwining maps are associated with the KG module homomorphisms. These 2 categories, representations of G with respect to over the field K and KG modules, these 2 becomes equivalent. Therefore, we can work in any one of them. Fine. So, in this point of view, note that if I loop K as a KG module via epsilon, the augmentation map, then that gives us the trivial representation of dimension 1. Dimension of a representation is the dimension of V. And number 2, KG as a KG module itself is just the regular representation. That justifies why we are talking about KG. Okay. Now, focusing more on KG, we had this augmentation map, and then consider IG to be the kernel of epsilon, and this is called the augmentation ideal. Naturally, the image is K, and therefore it becomes a maximal ideal. Moreover, one can check that this IG is actually generated by G minus 1, where G is not equal to 1. In fact, these form a basis of IG when G is not equal to 1 over K. Also, in view of these relations, hope I am correct. We can see that if G is generated by G lambda or some subset as a group, then IG is generated by G lambda minus 1 as both left and right ideal. Okay. Next, observe that with the help of basis elements, one can clearly check that KG is commutative if and only if G is abelian. In fact, even if G is not abelian, one can find out the center of KG, and that is equals to direct sum KZi, where I am specifying this element Zi, where if C1 up to CR are the distinct conjugacy classes of G, then Zi is sum of all the elements where X is in CR for all. Okay. And then, since I have remarked that G is already sitting inside the units of KG, therefore, one have a bijection okay. Moreover, this construction of KG is functorial in the sense that you send G to KG, and for any map G1 to G2 phi, you can define a map K phi from KG1 to KG2. That is just extending the map G1 to G2 via the basis linearly. And one can check that this construction gives a covariant functor. Moreover, from here we will actually compute some examples, particularly when G is finite abelian. So before that, suppose N is a normal subgroup of G, then observe that G to G mod N, the natural projection map, gives A pi from Kg to Kg mod N. And in this case, the kernel is generated by, so generally the kernel is generated by G minus 1, where G is in the kernel of phi as a group map. This again one can check with the help of basis. Okay. So here the kernel will be just the extension of In inside Kg. And this will give us the isomorphism which is again isomorphic to K tensor over K, K tensor over Kn, Kg. And these isomorphisms are all isomorphisms of augmented Kg algebras, augmented K algebras. Okay. So again, as an example, consider Kz. This is more or less the definition that this becomes the LoRa polynomial rings on one variable over K. And then in this case, the augmentation ideal is by the description above, generated by just x minus 1 because x is a generator. Okay. Similarly, if you consider the group algebra of Z mod dz, a finite cyclic group, in that case, via this description, one gets this as the group algebra. Any question? Okay. And in this case, the augmentation ideal is given by again x minus 1. Okay. Now, for a product of groups, one have these two inclusions, G1 to G1 cross G2 and G2 into G1 cross G2, call them I1 and I. So this via the functoriality gives us Aij from Agj to Kg1 cross G2. Now observe that elements in the image of Ki1 and elements in the image of Ki2 commute among themselves. Therefore, this extends to a K-algebra homomorphism from Kg1 tensoring over K with Kg2 to Kg1 plus G2. And this one sends G1 tensor G2 to G1 comma G2. And therefore, it sends a basis of the left hand side to a basis of the right hand side bijectively, and thus gives a isomorphism. Okay. So in view of that, so suppose now G is a finitely generated abelian group. Then by the structure theorem, G looks like Z to the power n direct sum cyclic groups of order D1, D2, etc., where this Di divides Di, Di plus 1 divides Di. Okay. So combining this one and that one at the extreme right gives us Kg to be, so put n many xn and xn inverse because of the z components, and then put m many yi's for the finite cyclic component, and the ideal is generated by y1 by y1 to the power d1 minus 1, y2 to the power d2 minus 1, and etc. ym to the power dm minus 1. In this case, the augmentation ideal will be generated by again all this xi minus 1 as well as this yi minus 1. Okay. Now, another important property of KG is that firstly, KG is a finite dimensional K algebra, and therefore, being finite dimensional K algebra, it satisfies descending chain condition from for both left modules and right modules, and therefore, KG is Artinian. By Artinian, I mean it is both left Artinian and right Artinian. Okay, and this will be used when we will go to Krull-Schmidt property, which will come later. Okay. Now recall that for a ring R may be non-commutative. By the Jacobson radical, we mean the intersection of left maximal ideals, which coincides with intersection of annihilator of simple left ideals, and thus become a two-sided ideal, which will again be equivalent to the intersection of all right maximal ideals. So I'm not going to that. Okay, and R is local if R has exactly one maximal ideal. Doesn't matter left or right, because in view of the Jacobson radical, if it is if it has one left maximal ideal, this is equivalent to say if it has one right maximal ideal. Same for two-sided. Okay. So for an Artinian ring, if R is Artinian, by Art I will mean Artinian ring. This Jacobson radical is the largest nilpotent ideal. These facts help us prove that KG is local, and we have observed one maximal ideal before. Therefore, local with maximal ideal IG, if and only if G is a P group. Okay, so maybe I will give a sketch of the proof. So if we assume KG is local, being Artinian, Jacobson radical is nilpotent, and therefore IG is nilpotent. So now choose K large enough so that IG to the power P to the power K becomes 0, and therefore for all G, G to the power P power K is equal to 1. Therefore order of each group element divides P to the power K, and therefore it is a P group. On the other hand, if you assume G to be a P group, then we have G mod the center. This is less than the order of G, and therefore by induction we can assume that I of G mod Z is nilpotent. And now note that because K G mod Z is isomorphic to KG mod IZ KG. Here Z means the center, by the way. This implies IG to the power n is contained inside IZ KG. And if you observe the, basis representation of IZ, then this commute and this is nilpotent. Therefore, because Z is an abelian group and we have this structure for the abelian groups, therefore we get IG is nilpotent as well. And IG is a maximal ideal. Being nilpotent, it must be the maximal ideal. Maximal nilpotent maximal ideal, I should say. Okay, so this one, this is because of the assumption IG is nil. No. Okay, fine. Sorry. Here I have assumed characteristic of A to be greater than equals to 2, and that is denoted by P. That was a mistake. Sorry. Okay. So as I have remarked earlier that Kg is commutative if and only G is abelian. For this case, yeah, because I have been using Artinian case, right? And that is not. Yeah. This is for the description. This does not need finite generation or something. But in this proof, I have explicitly used the Artinian condition because I have used this property that JR is the largest input. Okay. So as we have seen that Kg is commutative if and only G is abelian. Therefore, for the interesting cases, we must land into non-commutative rings. So for the next few minutes, I will just recall some property of non-commutative rings, therefore. Okay. So definition. So an R module M is called simple if it has no trivial, no non-trivial submodules, and it is called semi-simple, which henceforth I will denote by SS if it is a sum of simple modules. Now, with some John's lemma kind of argument, one can prove that for a ring R, the following conditions are equivalent. Number 1, R is semi-simple. Number 2, R is a, sorry, for a ring R and for a module M, M is semi-simple if and only if M is a direct sum of simple submodules. And number 3, if you have a submodule of M, then it is a direct summand of M. Okay. Also, we have one of the most important lemma in finite representation theory of finite groups, that is called Source lemma. So suppose M and N are two simple modules, simple R modules, and F is a map from M to N, then either F is 0 or it is an isomorphism. And that is very easy to see if you just consider the kernel and the image. As a corollary, what one gets is that if M is not isomorphic to N, then there is no homomorphism from M to N. And in the other case, for simple module M, this is a division ring. Okay. So in view of Source lemma and the definition of semi-simplicity, one can get the following results. Semi-simplicity is closed under taking submodules and quotients. That means submodules and quotients of semi-simple modules are semi-simple. Number 2, if M can be written as a sum of SI, where each SI is simple, then for any simple submodule, this S is isomorphic to SI for sum. Number 3, for the proof of 2, you can use this third statement. That this S becomes a direct sum, therefore it is a quotient, and then from some SI there will be the quotient map will be non-zero and therefore an isomorphism. Okay. Maybe I can give some exercise. So semi-simple module M is expressible as some SI where these SIs are finite if and only if length of M is finite. Length of M means that M has a finite composition series. And that is just a trivial corollary from Jordan-Holder theory. Okay. So as examples of semi-simple modules, trivial examples, any vector space over a field is semi-simple. Number 2, if you consider Z mod Nz, the cyclic group, this is semi-simple if and only if N is a product of distinct primes with multiplicity 1. We have a notion of semi-simple rings too, and that says a ring R is called semi-simple if R is a semi-simple left R modular. Okay. And using semi-simplicity of rings, one can define simplicity of rings. That is, semi-simple ring R is called simple if it has no non-trivial two-sided ideal. The nice properties of semi-simple and simple rings are the following: that R is semi-simple ring if and only if each R module is semi-simple. That is equivalent to say each R module is projective. Next, if R is a semi-simple ring, then R can be actually written as a direct sum of finitely many simple ideals. This finiteness comes from the fact that if you express 1 as summation xi, this will be a finite sum, and then those components from where these xi's are coming, they will give the whole decomposition. Okay, and therefore this says that up to isomorphism, there exist only finitely many simple R modules. Okay. Also, one have an Artinian condition associated to semi-simple rings, and that is the following. So, for a ring R, the following are equivalent, which says that R is semi-simple is equivalent to R being Artinian with Jacobson radical being 0, which says that, which is equivalent to R being Artinian and R has no non-trivial nilpotent idea. Okay. So one can say that R is simple if and only if R is Artinian and R has only one proper ideal. R has only one simple ideal. Corollary, if R is Artinian, R mod Jacobson radical is semi-simple. Actually, one can characterize all the semi-simple rings. That is because of the Artin-Mederman structure theorem. So this says that ring R is semi-simple if and only if R can be written as a finite product of matrix rings over division rings, where Di are division rings and this Ni, the number of components K and the Di's are all uniquely determined up to permutation and isomorphism. Therefore, a ring is simple if and only if it is just a matrix ring over a division. Okay, so having set up the basis, now we can formally move into representation theory. Okay, so we will start with two definitions. So a simple KG module is called an irreducible representation of G over K. And another concept is that a representation M of G over K is called indecomposable if someone can break M into two components as a direct sum N1 and N2, where this N1 and N2 are KG submodules, then this is the only case, or the other way around, that is up to permutation. Okay, now why am I talking about this indecomposable and irreducible? So first, let us see. Clearly from the definition, any irreducible is indecomposable. But the converse is not true. For example, suppose you are taking K Z mod Pz, where K has characteristic P. Then this one is containing the trivial representation. For example, if you take K to be Ft, then the trivial representation Ft 1 plus x plus etc. x to the power P minus 1 is sitting inside Fpz mod Pz. Therefore, it cannot be irreducible. However, one can check from the description there, that is Az mod Pz is Ax mod x to the power P minus 1, which in characteristic P will look like Ax mod x minus 1 whole to the power P, is indecomposable. That is because if you write it as a sum of two submodules are ideals in this case, and therefore from the structure theorem it will look like fx mod x minus 1 to the power P, direct sum gx mod x minus 1 to the power P. Now if you break it out, then you see that x minus 1 to the power P is divisible by both fx and gx, and then if you write 1 to be ax fx plus bx gx and raise it to the power P, then it will become 0 inside this kx mod x minus 1 whole to the power P, giving a contradiction. Therefore, we have seen an example where some module is indecomposable but not irreducible. Okay. But in zero characteristic, the story is different. That is because of the following theorem. In fact, this will cover a little bit of positive characteristic. So, for a finite group G, each short exact sequence of KG modules split if and only if order of G is non-zero in K. That is, in other words, either characteristic of K is 0 or P equal to characteristic of K does not divide the order of G. Okay, so let's see a proof of this. So consider a short exact sequence of KG modules here. Because it is a, short exact sequence of vector spaces, this will have a section, call it sigma. Sigma is a K vector space map. K vector space section. And now comes the important part why mod G is non-zero required. So consider sigma tilde of n to be 1 by mod G, summation G belongs to G, G sigma G inverse of n. Then one can check that this sigma tilde is a KG module section of the above short exact sequence. And this trick is called the averaging trick, which is one of the most important tricks in representation theory in zero characteristic. Okay, on the other hand, so I have proved that if order of G is non-zero, then everything splits. Now the other way around. So we have this short exact sequence. That means by the hypothesis this must split, call it sigma. Then we have sigma 1 to be some element of Kg of this form. And now one can see that since it is a Kg linear section, then sigma 1 is same as sigma of h times 1 because K is the trivial representation. And that becomes h times sigma 1, which will give you that Kg equals to A1 for all G in G. Therefore, one, which is equals to epsilon of sigma 1, now becomes A1 times epsilon G, but all of them are 1. Therefore, it is just A1 times order of G. That is equal to 1 means order of G is non-zero. Okay. So as a consequence, this one is the classical form of Maske's theorem. This says that for a finite group G, the following conditions are equivalent. Number 1, Kg is semi-simple ring. Number 2, K as Kg module via the augmentation map epsilon is projective. And number 3, order of G is non-zero in K. Again, for the proof, 1 to 2 follows from the property of semi-simple rings. And 2 to 3, previous lemma. And 3 to 1, again previous lemma, because if everything splits, that means everything becomes, every submodule becomes a direct sum. And therefore, this proof is done. Okay. So now, if we further assume that K is algebraically closed, then one can get the following results. Firstly, I should make some remark that in the case when Kg is a semi-simple rings, every sub-representation is a Kg submodule of some Kg module. So every sub-representation becomes a direct summand, and therefore one can check that every representation can be broken up into irreducible components. And that is an upshot of the properties of semi-simple. Okay. So here, first thing one can claim is that the number of non-isomorphic simple Kg modules, that is the irreducible representations, is the same as the number of conjugacy classes of G. And as a corollary, G is abelian if and only if each irreducible representation of G is one dimension. Okay, so no, I am now inside this case when order of G is non-zero in K. So here characteristic of K is either 0 or P equal to characteristic of K does not divide the order of G. Okay. And one more corollary from the source lemma in this case is that this is equal to K if P is an irreducible representation. Because this is a division ring over K, division algebra over K, and since K is algebraically closed, and one can see that D is here D equal to this endomorphism ring. This is here finite dimensional, therefore it must be equal to K. Okay. And this statement, in fact, generalizes to theorem due to Brouwer, which says that if K is algebraically closed and, okay, maybe I am writing it there. Okay, so if K is algebraically closed and characteristic of K is P, which is greater than equals to 2, then one can show that number of isomorphism classes of irreducible representations is the same as number of distinct p-regular conjugacy classes G. So by p-regular conjugacy classes, I mean that conjugacy classes containing p-regular element, and by p-regular element, I mean that elements whose order are not divisible by p. Moreover, if Kg is semi-simple, then the decomposition, I don't remember whether I remarked it earlier or not, of Kg into simple ideals actually characterize all irreducible representations of G over K. And therefore, one can safely say that if Kg is semi-simple, then there are only finitely many irreducible representations. Okay. G is to begin with anything. For P group, this is different than that statement. Because if it is not a P group, then P regular conjugacy classes will be equal to all the conjugacy classes. There will not be any P regular conjugacy classes. Or not exactly P group, if the group order is not divisible by P. That's what I mean. You were asking something else. Okay. So now we will deal with the story when Kg is not semi-simple. In fact, the starting point is that even if Kg is not semi-simple, for a finite group G, one can always say that G has only finitely many irreducible representations up to isomorphism. That is because of the Jordan-Holder theorem. So the Jordan-Holder theorem states that, I am writing some corollary of that. So if ring R is Artinian, that is, it has both. So Artinian implies Noetherian, that means it has both DCC and ACC, descending chain condition and ascending chain condition. Then for any finitely generated R module, we have a composition series like this. So call it such that the successive quotients mi by mi plus 1 is simple, and if we take another composition series, that will have the same length and the successive quotient will only differ up to permutations. That means they will be isomorphic up to permutations. Okay, so now if we consider any k and any g finite, then since kg is Artinian, therefore first observation is that every simple kg module is a quotient of kg. That is in general true for any simple R module, because you take an element x non-zero and then consider Rx. This will be whole of the module. Therefore, it is a quotient of kg. And that means this appears in a composition series. Therefore, this call it S. S appears in a composition series. That is because you start with S and then you have this kg, and below that the kernel of the surjective map from kg to S, and that is again finitely generated, and then keep going down. Okay. Fine. And therefore, by Jordan-Holder theorem, this S must be simple quotient. We know that there are finitely many of them. Fine. So now, if we have seen that if kg is semi-simple, then in view of Maske's theorem, every representation M can be written as a direct sum of all of these things are irreducible representations. That is the point of the whole semi-simple modules. Okay. Now, let us see whether it is true in general or not. So, for example, take again K to be a field of characteristic 2 and consider K Z mod 2. Then observe that the trivial representation, that is again this is Kx mod x square minus 1. So the trivial representation K1 plus x is the only one-dimensional sub-representation of this Kz mod 2z. And therefore, being the only one-dimensional sub-representation, we can clearly say that Kz mod 2z cannot be broken into indecomposables. Because if it is a non-trivial one, then both of them must have dimension 1. Okay. I'm sorry, irreducibles. Okay. Therefore, we go into the point of view of Krull-Schmidt. Now, what does Krull-Schmidt say? Krull-Schmidt says that every representation under some certain hypothesis can be broken into indecomposables. Therefore, we are shifting our attention from irreducibles to indecomposables. Okay. So definition: ring R is said to have the Krull-Schmidt property if firstly for any finitely generated R module, M can be broken into finite number of indecomposables. And secondly, if we have two decompositions of M, then we have the number of components to be same, and after a permutation, Mi is isomorphic to Ni for all I after a permutation. Okay. Now, theorem of Krull-Schmidt, or sometimes it is called Krull-Schmidt theorem. This says that every Artinian ring has this property. Every Artinian ring have, I am writing in abbreviation, Krull-Schmidt property. Therefore, specializing to Kg, I have been repeatedly telling that Kg is Artinian. Therefore, Kg, irrespective of the fact whether all the representations can be written as a direct sum of irreducibles or not, it can be written as a direct sum of indecomposable. Therefore, it makes sense to study indecomposable modules. Okay. But in general, there is no guarantee that there will be finitely many indecomposable like those for irreducibles. Okay. So therefore, the following definition. Suppose K is an infinite field and lambda is a finite dimensional algebra. Then lambda is of finite representation type if there are only finitely many indecomposables up to isomorphism. There are other representation types as well. The next one is M representation type. If firstly it is not of finite representation type, plus for all n, for all dimension n, there is a finite set of lambda kt bimodules, where kt is the polynomial ring, Mi, where all these are P as right kt modules, okay. And it is said that all except for a finitely many indecomposables over lambda of dimension n are of the form Mi tensor taken over kt M for some I. Since these MIs are lambda kt bimodules, therefore from the left hand side we get a lambda module structure on that. Okay. And where this M are indecomposable kt modules. Okay. Now in this definition, we are requiring this set, this finite set Mi depending on each n, and if we let them grow independent of n, if the set Mi can be chosen independent of n, we call it domestic representation. So we say lambda is of domestic representation type. This one. Yeah, so I am saying lambda is of tame representation type if firstly it is not finite representation type, and for each n there exists a finite set of lambda kt bimodules mi, where these mi's are required to be free as a right kt module, and except for a finitely many, all the indecomposables over lambda of dimension n can be written as a tensor of mi and m over kt, where m is a indecomposable kt module. So it is a left lambda module and right kt module, and those two are commutative. And the last one is that lambda is of wild representation type if there exists a finite lambda k xy bimodule m, again free as a right kxy module, and if I take this functor m tensor over kxy, okay. So in this view, we have the trichotomy theorem. So we have the trichotomy theorem, which actually classifies all the finite dimensional K algebras, or KG in particular, with respect to their representation types. So here G is a finite group and K is an infinite field of characteristic P, obviously greater than or equal to 2. Then AG has finite representation type if and only if G has cyclic P subgroups. Number 2, KG has, okay, so I am taking this KG has. This has domestic representation type if and only if, first of all, P equal to 2, and then we will talk about the silo 2 subgroups, and any silo 2 subgroup of G is isomorphic to the Klein's 4 group, which is Z mod 2 plus Z mod 2. Number 3, it has stem representation type if and only if, again P equals to 2, and for any silo 2 subgroup of G, H is either isomorphic to the dihedral groups. So I use this symbol D2N for dihedral group of order 2N. And or it is semi-dihedral groups. So symbol is D2 to the power N, and that is the group generated by two elements with the relations a to the power 2 to the power n minus 1 equal to x square equal to what, and x equals to a to the power 2 to the power n minus 2 minus 1. Or it is the generalized quaternion groups, again generated by two symbols but with different kind of relations. And except for these cases, in all the other cases, KG has wild representation type. D2N, this 2N represents the order. So it is, so D2N means this. This one. Huh? Yeah, D2N has a two silo group, right? In fact, depending on N, there could be plenty of. No, D2N I am writing. Just 2N. Okay. N could be some power of 2. Okay, I got your concern. N could be some power of 2. Okay, so if you want that, fine. Okay, and AG has wild representation type in all the other cases. Okay. Also, there is a connection between, so what we are talking about is basically the differences between indecomposable and irreducibles, but they are not entirely different. In fact, there is a connection which says that projective indecomposables are in 1-1 correspondence with irreducibles. So the theorem is, if R is a finite dimensional K algebra, then the association P goes to P mod Jacobson radical of R times P gives a 1-1 correspondence between isomorphism classes of projective indecomposables and isomorphism classes of, okay, I am talking about general K algebra, so I am using this terminology, simple R modules. So therefore, we have seen that for a Artinian case, these simple R modules, there are finitely many of them up to isomorphism. Therefore, we can say that in this case, there will be finitely many isomorphism classes of projective indecomposable modules as well. And in particular, this applies to KG. I would like to stop here, but before that, I will give some reference. Okay, so for the first part, what I was saying, basic theory of representation, probably Said's book, linear representation of finite groups, is a nice one to begin with. And then most of the materials I have followed from Professor Iyengar's lecture notes. That is called Modules and Cohomology over group rings, and this is available at the MSRI website. And here you will get even more examples of what I was talking about, and for this proof, he has constructed something called projective covers and then moving towards group algebras, homology of group algebras. Okay. Most of the parts I have talked about for semi-simplicity is available at Lang's algebra. For the Brouwer's theorem, I was going through the notes of Professor Amritanshu Prasad, which is titled Representation Theory of Finite Groups. In positive characteristic. And for the last result, this bijection between projective indecomposables and simples, I was going through Professor Leinster's notes on bijection between projective indecomposable and simple R modules, where R is a finite dimensional K algebra. And this is available at the archive. So I'll end.